All right, so let's start solving this problem and obtain the shear and bending moment diagrams for this case. So we'll start with our general solution. And the first thing we have to do is obtain the free body diagram and external reactions that support the beam. So let's do that. Let's draw the beam by itself when we draw our free body diagram. Let's draw the corresponding loading that would go along with it. That line like that. And let's draw all the loadings that are present. We don't want to skip any of these. And of course, we want to draw the actual reactions at the walls. So I'm going to draw them all to be positive in this case. So I'm going to have the reaction By, Bx, and our external reaction at the wall, Mb. We perform our static analysis and obtain our calculation. So we can confirm that through some of the forces in x, Bx is equal to 0. We confirmed through some of the forces in y that we will have By pointing positively minus 100 kip per foot. We convert the length of the beam from 24 inches to feet to make sure our units are consistent. Set that equal to 0, and By is equal to 200 kip. We sum the moments. I'm just going to sum the moments about B. And following the right-hand rule, we obtain that we have minus 100 kip foot from the couple at A. We have plus 100 kip per foot over 2 feet times the moment arm, 1 foot, plus Mb equal to 0, so that our external moment at B is minus 100 kip foot. So I assume the wrong direction on that one, but I can take care of that when I draw my loading diagram. So to start that, I'm going to put this on this other page, but imagine that it's the next one that follows up. So I'm going to go ahead and draw my loading diagram. Okay, we draw our external loads on it. Because they are going to show up as different behavior on our shear and bending moment diagram. This is 100 kip per foot. We have our external couple of 100 kip foot. I have By existing, which is 200 kip. And I'm going to turn the direction of Mb because I found out it was negative. So I'm just going to draw it as it is, which is 100 kip foot. Now we are ready to start calculating what our internal loading is. And what we're going to do is we're going to section the beam somewhere between the points of discontinuity. So to do this, I'm going to go ahead and establish that I'm going to analyze my section. Oops. A, B. I'm going to draw the section of the beam that I'm interested in, which doesn't have to be the whole beam. It has a portion of the distributed load that I see is still at 100 kip per foot. It shows my external couple of 100 kip foot. And I will have on this section my internal shear between A and B as a function of x, and my internal bending moment, MAB, as a function of x. At this point also I want to keep in mind that my cut didn't happen all the way to B, it happened at a distance x from the start to the beam, and that's the x that is going to let me express the shear and bending moment as a function of the length of the beam. Here we can now perform the static analysis that goes here. So let's do this one. And we do sum of the forces in y equal to 0. And I would have minus BAB of x minus 100 kip per foot over the length x equal to 0. And I would have sum of the moments about the cut equal to 0. Okay, now we can calculate the internal bending moment, and we have MAB as a function of x. We have minus 100 kip foot from the external couple, and we don't forget that we have plus the force happening at the distributed load here, which is 100 kip foot times x, which x now being feet, ensuring that we have kips, and the centroid of that region, which would be x divided by 2, and that would be the distance to the cut. The whole thing is equal to 0. And once I solve these two things, I obtain that shear between A and B as a function of x is equal to minus 100x kip. And I obtain that the bending moment between A and B as a function of x is equal to minus 50x squared plus 100 kip foot. We are now ready then to plot these as a function of x. We go ahead and choose our axis. I'm going to go ahead and choose green for that one. This would be my shear in kips. I start checking the discontinuities at A. There are no discontinuities at A, so I start at 0 kip. And following my graph, I go to the next discontinuity at B, which after 2 feet results in minus 200 kip. Because there is a point load happening at B, this causes a jump on my shear diagram of 200 kip, landing back at 0. This is, in effect, BY. We are now ready to do the same thing, our bending moment diagram. We go ahead and draw our axis. Forgot to put that over there. This would be my bending moment in terms of kip foot. I'm going to have my axis in terms of x, and I'm ready to draw my bending moment. Now, a quick recall from class. Remember that if I have a cut starting from the left and the cut being on the right, means my internal bending moment as a function of x will be positive this way. And if I were to have an external moment being applied, then the internal bending moment would be the negative of the external moment. That means when I have a negative couple acting at A, it would result in a positive jump from 0 to 100 kip foot at that location. And if I were to follow up the way to my next discontinuity, I will use my M of A equation, M of AB equation, and I plug in x equal to 2, resulting in minus 100 kip foot internal bending moment. This is, however, not a straight line. This is a parabolic line. And because it's concave down, we can plug in internal values. If we were to plug in x is equal to 1, for example, we'll give us an idea of where it went. And we are able to do the plot. Now, this doesn't end at 0, but we do have another external reaction, 100 kip foot on the negative direction, according to my right-hand rule, resulting in another positive jump of my bending moment diagram, and we land at 0. So now for this problem, we have come up with the loading diagram here. Our shear diagram and our bending moment diagram.